Hello all. In this video, we're going to take a look at different categories, different kinds of machine learning tasks, and in particular, supervised versus unsupervised and reinforcement learning and all of those things. We will also take a closer look at supervised learning and just how that process works, like how do you go about training a model for a supervised learning task and things like that. All right, so going back to my notes, different kinds of machine learning. These are really different from each other. Uh, Although I guess there are two here that I consider really part of the same thing, but people argue about this a lot. And we categorize these general categories of approaches based on the kind of feedback that the machine learning system is given about its task. So the first and by far most common is supervised learning. A large percentage of what happens in machine learning is supervised learning because it's the easiest. And certainly most AI people, this is what we're thinking about. So what feedback is it given? Well, with supervised learning, we present an input and the model will do its best to produce an output, but we know what the correct output should be. So the machine learning algorithm learns by being shown the correct output after it's produced its own, and then modifying its understanding of the patterns so that it will be closer to producing the correct algorithm. So supervised learning, that's sort of a description of how neural networks work, but generally with supervised learning, the system is given both the input and the correct answer, and it looks for a way to connect those, to predict the correct answer given the input. This requires a lot of work on our part. Creating a data set for supervised learning is more complicated than creating a data set for some of the others. A good example of this would be if you're training a robot car to drive on a track, and what you do is record a human driving the robot car on the track, and then you have the robot replicate what the human would do. So predict what action to take based on the input. But it's already been told what the human did, and that is the right answer for it. It's supposed to replicate the human's behavior. So that's supervised learning. There is a new term that has come into vogue called self-supervised learning. Sometimes this approach gets categorized as unsupervised learning, but I'll argue with that. I don't think that's actually the best way to describe it. And why this is important is that self-supervised learning is frequently what happens with chatbots and other models like them. So it's a big segment of what people do with machine learning right now, and it's slightly different from supervised learning, but to me it's a special case of supervised learning. So what are we doing here? The target values are somehow an intrinsic part of the data itself, which means we as the creators of the data set, we don't have to go in and label the data. It's just a part of what the data has. And so we can collect the data together and then just feed it into the model. But the model's learning is still based on targets, on having a known target that it's trying to replicate. And that's where I think it fits more under supervised learning. So there are examples of these encoder-decoder models that do auto association. That's one term for it. Fundamentally, the idea is you feed in an input to the model, it processes it, and the goal is for it to output the same input, to replicate in the output what the input is. Why would you do that? Well, typically, somewhere in the middle of these encoder-decoder models, there's a bottleneck. It has to somehow condense or compress its representation of the input data and then unpack it to produce the same thing in the output. So it's a way of getting a method for compressing data and for encoding data in a more compact form for whatever purpose. It's also central to things like image generators. So image generator models, which are always fun to play with, they take actual images in, and they're expected to output an image like it, and in the middle there's a condensed representation, and then we can pull that model apart and feed in other data to the decoder phase and have it actually produce new images that way. We'll talk more about that later. The other place that you see self-supervised learning is fundamentally what large language models do. So what they are asked to do, the way they are trained, is they're given, say, text, sequential data like text, and they are asked to predict the next word. So given some part of a sentence, predict what the next word might be. So if I said to you, once upon a time I went, and then I said, what's the next word going to be? There are lots and lots of possibilities, but it's been trained on text where we had that text, we knew what came after the word went. So that was the target that it was trying to hit. And there are definitely places where it's easy, this is an easy task, and places where this is a very complex task, and where there could be lots of different words that follow. But fundamentally, that's how a large language model works. Given a sequence of text, predict the next word. You can use it to generate text then, because once it's predicted the word, you say, okay, well now if it's an output that word, let's look at that sequence now, including the word it just generated, and predict the next word after that, and so on and so on and so on. So it can actually generate text by one word at a time, predicting what should come after what it has said already. Now, large language models have several stages of their training that are quite complex. This is the heart of the underlying model, but it does go through other stages of training and different kinds of training too. All right, other main categories that we have, reinforcement learning. We are going to take a look at this more closely in a little bit, but just for now, it's difficult but really, really interesting. The system is given an input, and it chooses some action, and then it is rewarded or punished based on the results of that action. It is not told the right answer, but it is given feedback, given a reward that represents the quality of what happened because of its action. So this would be, unlike the earlier instance with supervised learning where we were training a robot car to drive on a track, and we gave it data of a human driving the car on the track, and it was supposed to replicate it. Here, this would be an online learning system. So the robot car would be trained to drive on a track by putting it on the track and having it randomly choose actions to take and reward it when it stays on the track and moves forward, and punish it if it goes off the track or something like that. So it's a totally different way of thinking about learning, but it's also super interesting because it doesn't require us to provide it with a model of what the correct answers are. Unsupervised learning is the final one. It's kind of taking it all the way to the other end of the spectrum. You give the system input examples, and you don't give it any goal, and you don't give it any feedback. It just tries to find patterns in the input examples. So clustering of various kinds is the most common kind of algorithm, and there are lots of different ways that people do this. If you want to learn more about it, go and do like the statistical machine learning. It's much more of a tool for data science than I think for straight up AI, although I'm sure there are people who work on this in AI. There's some other things besides clustering. There was a neural network model in the olden days. It was called a Cahonin network. They had another name for it because Cahonin didn't like having their name on it. But fundamentally, It tried to produce outputs where similar inputs were placed spatially similar in a similar location, but otherwise it wasn't given any target. And so it would kind of learn to categorize things into regions of the space, which was really an interesting model. There are deep learning systems these days that leverage a small supervised learning data set and extend it to a larger unlabeled data set. So these are kind of semi-supervised is the term that gets used, or semi-unsupervised. So they're trying to extrapolate from a small set of data that they have the targets for to label data they don't have the targets for. And there's some really interesting approaches there, including efforts to learn one-off. So given one example, can we find ways to get the models to find patterns? At this point, I'm going to focus in a little bit on supervised learning, because that's what we're going to spend most of our time on. And we'll talk a little bit about the process and some particularities that you need to look for with supervised learning. So again, with supervised learning, we build a training set that has input examples, and for each input example, we have the correct output, whether that's a category or a number or whatever it might be. And our algorithm's job is to find patterns and regularities in the data that allow it to infer or predict the output given the input alone. Now, there's various terminologies and notations that get used here. So when we talk about a training set, we talk about it as being a pair, an X for the input and a Y for the target. And so you'll see examples where we're using X and Y in machine learning examples, and that's what that's sort of an understood piece of notation. So X is some set of n different examples, and Y has to have one value for each example, which is the correct output for that example. All right, our machine learning algorithms build a model. Given this training data set, they're going to construct a model one way or another, and with the goal that they give the correct answer for each of these inputs, that they actually produce the correct target. But that's not enough. That's actually not that hard to do. You could just memorize the data, and every time you see X2, you go and look up Y2, and that's great. What we want, the key central goal for any machine learning system, is generalization. Because we can't possibly train most systems on every possible situation or input they could ever see. We want to train them on a set of data and then have it work well on data it has never seen before. So that's generalization, and that's what's critical for any machine learning system. So when we evaluate them, that's what we're evaluating them on, is how well do they do on examples they were not trained on. So that's, as we go forward, that's the focus to keep in your head. We want things that work well across all examples. And we accept that the model is likely to do really, really, really well on the training data, the data it has been using to build its model, and it's going to do less well on things it hasn't seen before. But what we want is to avoid a huge drop so that it only performs well on things that it has actually seen explicitly before. All right, then just kind of connected to that idea, we have two terms that we use about the performance of the model. So I'm going to start with underfitting, even though it's below the other one. Underfitting is when the model fails to learn the task. So a model is underfitting if it's not performing well even on the training data. Even on the examples that it's seeing, it's just not doing a good job. There are lots of reasons why this could be happening. Oftentimes we have to change the parameters or switch algorithms in trying to find one that works well on the data. But it is something to look for. If you just have general bad performance all across the board, then the model is underfitting. The bigger problem that we have very frequently is overfitting. And this is when the model is I like to think of it as it's almost memorizing its training data. So it's finding features in the training data that allow it to do a better job of predicting the output for the training data. But those features are actually irrelevant to the task in general. And it performs much, much worse when given examples that it hasn't seen before. And you see this divergence in performance. So it has a very, very, very high accuracy on its training data, but when you try it on other data, you get a really big gap. It's a big problem. People have worked on algorithmic solutions. So you take a basic algorithm for machine learning, and then you start adding to it and tweaking it, trying to avoid having the model overfit. When we work with neural network models or deep learning models, we look for this pattern of overfitting, and we make changes to the model, to the algorithms it's using, to whatever we need to try to avoid overfitting. Overfitting corresponds to a lack of generalization. And underfitting typically just means it can't even memorize the data set. All right, so suppose you wanted to do some supervised learning. What would that look like? I have some steps here. We'll kind of talk through those, and then that'll be it for this particular video. So the process of setting up and training your data, your machine learning algorithm. First step is to build a data set and label each example with the correct answer. Remember, we're talking about supervised learning. This is part of what you do. Or you can find an existing data set and use it instead. So there are a lot of data sets posted on the web. It's really common to go find one and adapt it for your own uses, because this is an incredibly time-consuming process, particularly if you're using deep learning models. You need a much larger amount of data for those models to be able to learn effectively, and they'll do better the more data you give them. So you have to build a really big data set. Big research projects or commercial projects that are doing this kind of deep learning, they often hire people to do the data labeling because it is such an onerous task. And in fact, there's a whole big ethical issue around how those data sets get created, because when they hire people, it's often done through something like TaskRabbit. It's done piecework style, so they get 3 cents for every labeled instance that they do, which doesn't always work out to a good wage when you work out how much time it takes. And some of these data sets may be for things that are somewhat disturbing. So for instance, a lot of social media companies would really, really like to automate the task of identifying violent or pornographic images that get posted to social media. But the problem is, because right now the problem is that humans have to do that identification in many cases, and it's traumatic for the people who are involved. They spend all day looking at pornographic or oftentimes violent images and having to make decisions about whether they should be allowed or not. Automating the system sounds like it's a great idea if you can build a good enough machine learning model, but the problem is, in order to train the machine learning model, you have to build the data set, which involves human beings labeling that data over and over again. So this is a big issue. Building the data set is a huge component. It can take a lot of time. I know in my own work with the image data that I've been working with the last few years, I've spent literal weeks with my summer research students developing our data set. It's a lot of work. All right, but let's say you have your data. Whether you get it somewhere or you build it yourself, you have some data. Depending on what machine learning algorithms you're going to use, you may have some pre-processing of that data that needs to happen. Rescaling data so they all lie within the same ranges. Doing some principal components analysis or other sorts of things to simplify the data, to reduce the size and quantity of the data. There's lots of pre-processing that may have to happen next. If you're working, say, with images as I do, maybe you have to standardize them so they're all the same size. The next step before you run the machine learning algorithm is dividing the data into at least two, but ideally three parts. When you're doing a small project that's just a little experiment, two is probably enough. But for an actual research project, three would be ideal. All right, so what are these three parts? The first and largest is the training data. This is the portion of the data set that the algorithm is actually going to see. And that's usually, say, at least 60% of your data, more often 70, 75, 80% of your data is going to be used for training. You have to be really careful that, by the way, that you're selecting elements for these different parts at random so that you have an even distribution of all the different situations in your data set across all three of these sets. All right, so besides the training data, there is another set called the validation data. Validation data is not shown to the model while the model is learning, but we use it to assess the quality of learning of the model, how well it's generalizing. It's there to validate the generalization of the data of the model. So we also can use it as a way of testing whether the model is overfitting. So there's an iterative process in here, which is under my last data point. So where you train the model, you test it on the validation data as well as the training data, and then maybe it's not performing quite like you like, so you change something about the model. You tweak one of its parameters, you try changing to a different model, and you do this again. Over and over and over, you are using the validation data to evaluate the model as you're creating it. And at the end of that process, you have your final model, which, when you're done with all of those iterations of training, the testing data is the smallest of the three parts, and it is held back for the use once you are done training. So once you've finished that iterative process of trying a model, tweaking it, trying it again, tweaking it, changing models, all of those sorts of things, you get your final model that you think you're all done with, you have in reserve a set of test data that has never been used. It was not used to train the model. It was not used by you to validate the model. Why would you need this? Well, because in that iterative process, as you were tweaking and trying again and tweaking and trying again, you may well have input into the model some bias related to the validation data. So there could be a lack of generalization that's coming from the fact that you were involved in the process, choosing the parameters, choosing the model, and you were basing that on this validation set. So to avoid that model bias toward the validation set as well as its training set, you test it at the last step with data it's never ever seen and was never used as part of the validation process. And it's like a sanity check. Did it actually generalize? How well does it work on things it's never actually ever seen before that I didn't use for anything? If you have a small project, we sometimes just omit that test set and we just worry about training and validation. But if you're going to do a larger project, you need to take seriously this extra requirement. All right, so then the last step is what I talked about before, this iterative process. You run the algorithm, you evaluate the results, you run the algorithm again, you evaluate the results, and you see what happens. One of the things you have to be very careful about is you want to make sure that on any run of the algorithm, it only sees the training data and that these training and validation sets are clearly separate. Particularly with models that have an iterative training process like neural networks, you can fall into a trap where you train the model on one day with training data, and then the next day you want to train it some more, and you regenerate the training data with a different split of training versus validation, and now your model has seen most of the data, and so it's actually not a valid model anymore. So you have to be really careful about how you isolate training and validation data, and make sure that you have the same training and validation data across your experiments. Okay, I'm going to stop here. And in the next video, we will talk through the various tools that we use and the various mechanisms and formulas we use to evaluate these machine learning models. Until then, I will see you very soon.